Atoms are the fundamental building blocks of matter, and understanding their nature is key to grasping the structure of the universe. To fully appreciate the complexity of atoms, it's essential to delve into their composition, history, and role in everything we observe, from the smallest particles to the largest cosmic structures. Atoms consist of three primary particles: protons, neutrons, and electrons. Protons and neutrons make up the nucleus, while electrons orbit this central core. The arrangement of these particles defines not only the atom itself but also the properties of elements. Protons have a positive charge, while electrons are negatively charged. Neutrons, as the name suggests, carry no charge. Despite their small size, these subatomic particles hold incredible power and potential. The interaction between them governs much of the behavior of atoms, leading to chemical reactions, bonds, and the formation of molecules that make up all matter. The story of how we came to understand atoms dates back to ancient Greece. Philosophers like Democritus proposed that everything was made up of tiny, indivisible units called atomos. Though lacking the technological means to prove their theories, these early thinkers laid the groundwork for what would become atomic theory. It wasn't until the 19th century that significant strides were made. John Dalton, an English scientist, formalized the idea that atoms were the smallest indivisible components of matter. His atomic theory, published in 1808, proposed that each element consists of identical atoms, which combine in fixed ratios to form compounds. This marked a significant step forward in our understanding of chemistry. As we ventured deeper into the structure of atoms, discoveries began to challenge Dalton's notion of indivisibility. In 1897, J.J. Thomson discovered the electron through his experiments with cathode rays, proving that atoms were not the smallest particles but could be divided further. Thomson's plum pudding model suggested that atoms were made of a positive soup, with negatively charged electrons scattered within it, much like plums in a pudding. This model, however, was soon replaced by a more accurate representation. Ernest Rutherford's gold foil experiment in 1909 led to the discovery of the atomic nucleus. By bombarding thin gold foil with alpha particles, Rutherford observed that some particles bounced back, indicating that atoms had a dense, positively charged center. This discovery was monumental, as it revealed that most of an atom's mass is concentrated in its nucleus, with electrons orbiting around this dense core. The model of the atom continued to evolve with Niels Bohr's work in the early 20th century. Bohr proposed that electrons orbit the nucleus in specific energy levels, or shells, rather than randomly. His model introduced the idea of quantization, where electrons could only occupy specific orbits with distinct energy values. This explanation helped account for the discrete spectral lines observed in atomic emissions, further solidifying the understanding of atomic structure. However, the quantum world is complex, and the behavior of particles at this scale is far from intuitive. As quantum mechanics developed, it became clear that electrons do not travel in neat, defined orbits as Bohr initially thought. Instead, they exist in regions of probability known as orbitals, as described by the Schrödinger equation. This discovery was crucial in understanding how atoms bond with one another and form molecules. The electron cloud model, which replaced the Bohr model, illustrates the probabilistic nature of electrons' positions around the nucleus. One of the most significant breakthroughs in atomic physics came with the discovery of isotopes. Isotopes are atoms of the same element that contain different numbers of neutrons. This distinction is important because it affects the stability of atoms. Some isotopes are stable, while others are radioactive, meaning they decay over time and emit radiation. This discovery opened up a new field of study, leading to advances in nuclear chemistry and medicine. The study of radioactivity, initiated by Henri Becquerel's discovery of spontaneous emission from uranium salts, was further expanded by Marie and Pierre Curie. Their work on radioactive elements, such as radium and polonium, demonstrated the incredible energy stored within atoms. The Curie's research laid the foundation for the development of nuclear power, as scientists began to unlock the potential of atomic energy. In 1932, James Chadwick discovered the neutron, adding another piece to the puzzle of atomic structure. The neutron's role in the nucleus was essential for maintaining the stability of atoms, particularly in heavier elements. This discovery was critical to the development of nuclear fission, the process by which an atom's nucleus splits, releasing vast amounts of energy. Nuclear fission would later play a key role in the development of atomic energy and weaponry. One of the most famous applications of atomic theory was the Manhattan Project during World War II. Scientists like J. Robert Oppenheimer, Enrico Fermi, and others worked on developing the atomic bomb, which harnessed the power of nuclear fission. The bombings of Hiroshima and Nagasaki in 1945 showed both the destructive potential of atomic energy and the necessity of understanding and controlling this powerful force. The post-war era saw the development of nuclear power as a potential energy source. Unlike fossil fuels, nuclear energy produces minimal greenhouse gas emissions, making it an attractive option for reducing humanity's carbon footprint. However, concerns about radioactive waste, the potential for catastrophic accidents, and the proliferation of nuclear weapons continue to be debated. Atomic theory also plays a vital role in the development of modern technology. Semiconductor devices, which form the basis of computers and other electronic devices, rely on an understanding of atomic behavior in materials like silicon. The discovery of quantum mechanics has enabled advancements in fields such as quantum computing, where the principles governing atoms and subatomic particles offer the potential for exponentially greater computational power than traditional binary systems. Atoms are not just relevant to human-made technologies. They are the building blocks of the universe. Stars, for example, generate energy through nuclear fusion, a process where atoms fuse together under immense pressure and temperature to form heavier elements. This process, occurring in the hearts of stars, is responsible for the creation of most elements in the periodic table, including those essential for life. As our understanding of atoms deepens, new questions continue to arise. What lies beyond the atom? Subatomic particles, such as quarks and gluons, are being studied to further comprehend the fundamental nature of matter. Particle accelerators, like the Large Hadron Collider, are used to smash atoms together at incredibly high speeds, allowing scientists to observe the behavior of these particles and search for new ones, such as the Higgs boson, which was discovered in 2012. The study of atoms has also led to advances in materials science. Nanotechnology, which involves manipulating atoms and molecules to create new materials and devices, is revolutionizing industries from medicine to electronics. By controlling matter on the atomic scale, researchers are developing stronger, lighter, and more efficient materials with a wide range of applications. Atoms are the foundation of everything in existence. From the ancient philosophies of Democritus to the cutting-edge research of today, our understanding of atoms has come a long way. The study of these tiny particles has unlocked immense power, both for good and for ill, and continues to drive scientific and technological advancement. As we probe deeper into the quantum world, the mysteries of atoms and their behavior will undoubtedly yield even more surprising and transformative discoveries. As we continue our exploration of atoms, it becomes increasingly clear that they are not only the building blocks of matter but also the keys to unlocking some of the most profound mysteries of the universe. Atoms, with their seemingly simple structure, hold within them the secrets of the fundamental forces that govern everything from the behavior of particles on a quantum scale to the birth and death of stars. The more we investigate the nature of atoms, the more we uncover about the universe's past, present, and future. One of the most intriguing aspects of atoms is the way they interact with one another to form the vast array of materials we encounter every day. Atoms can bond with each other in a variety of ways, depending on the arrangement of their electrons. The forces that govern these interactions, such as covalent, ionic, and metallic bonds, determine the properties of materials, from the hardness of diamonds to the conductivity of metals. These bonding interactions are driven by the quest for stability, as atoms seek to achieve a balanced configuration of their outer electron shells, often referred to as the octet rule in chemistry. Understanding these bonds is crucial to many scientific fields, especially chemistry and materials science. When atoms form molecules, they give rise to the substances that make up our world. Water, for example, is a simple molecule formed by the combination of 2 hydrogen atoms and 1 oxygen atom. Yet this simple arrangement gives water its remarkable properties, such as its ability to dissolve a wide range of substances, its high surface tension, and its capacity to store and transfer heat. These properties, in turn, make water essential for life as we know it. However, atomic bonds are not just limited to simple molecules. Complex compounds, such as proteins, DNA, and other macromolecules, are all products of atomic interactions. The vast diversity of life on Earth is a result of the different ways in which atoms combine and recombine to form the building blocks of life. Proteins, for example, are composed of long chains of amino acids, each with its own specific arrangement of atoms. The sequence of these amino acids determines the structure and function of the protein, which in turn plays a crucial role in the biological processes that sustain life. In the realm of biology, understanding atomic interactions is essential for understanding how cells function. Atoms and molecules are the fundamental units of biological processes, from the replication of DNA to the transmission of signals between neurons. The chemistry of life is, at its core, the chemistry of atoms, and the study of biochemistry is essentially the study of how atoms and molecules interact within living organisms. The role of atoms extends far beyond the realm of biology, however. Atoms are also the foundation of our understanding of the physical world. In physics, the study of atoms has led to the development of numerous theories that explain the behavior of matter and energy. Quantum mechanics, for example, emerged from the study of atomic and subatomic particles. This branch of physics deals with the behavior of particles on an extremely small scale, where the classical laws of physics break down and new, often counterintuitive, rules take over. One of the most famous examples of quantum mechanics at work is the phenomenon of superposition, where particles such as electrons can exist in multiple states at once. This idea, first proposed by Erwin Schrödinger, challenges our traditional understanding of reality, and has profound implications for fields like computing and encryption. Quantum computing, which takes advantage of superposition and entanglement, promises to revolutionize the way we process information, offering computational power far beyond the capabilities of classical computers. In addition to quantum mechanics, the study of atoms has also led to breakthroughs in our understanding of energy and thermodynamics. The concept of energy levels in atoms, for example, helps explain how light is emitted and absorbed by matter. When electrons in an atom absorb energy, they jump to higher energy levels. When they return to their original levels, they release energy in the form of light. This process, known as electron excitation, is responsible for phenomena such as the colors of fireworks, the glow of neon lights, and even the light emitted by stars. Speaking of stars, atomic theory plays a crucial role in our understanding of how they form and evolve. Stars are essentially massive nuclear reactors, where atoms undergo fusion to produce heavier elements. In the early stages of a star's life, hydrogen atoms fuse to form helium, releasing vast amounts of energy in the process. As the star ages, it can fuse heavier elements, eventually leading to the formation of elements like carbon, oxygen, and iron. This process, known as stellar nucleosynthesis, is responsible for creating most of the elements found in the universe. When a star reaches the end of its life, its fate depends on its mass. Smaller stars, like our Sun, will eventually shed their outer layers and become white dwarfs, while more massive stars can undergo supernova explosions. During a supernova, the star's core collapses, and the energy released can create elements even heavier than iron, such as gold and uranium. These supernovae scatter these elements across the cosmos, seeding future generations of stars and planets with the building blocks of matter. In this way, the atoms that make up everything on Earth, including our own bodies, were forged in the hearts of stars billions of years ago. But atoms don't just tell the story of the stars, they also tell the story of the universe itself. The study of cosmic background radiation, for example, has provided evidence for the Big Bang, the event that created the universe roughly 13.8 billion years ago. In the moments following the Big Bang, the universe was a hot, dense soup of particles, including protons, neutrons, and electrons. As the universe expanded and cooled, these particles began to combine to form the first atoms, primarily hydrogen and helium. Over billions of years, these atoms came together to form the first stars and galaxies. As stars went through their life cycles, they created and dispersed heavier elements, which eventually formed planets, moons, and other celestial bodies. Today, we are able to study these atoms using advanced technology, such as the Hubble Space Telescope and particle accelerators like the Large Hadron Collider. By examining the light emitted by distant stars and galaxies, scientists can determine the composition of these objects and gain insight into the history of the universe. Despite all that we have learned about atoms, there is still much we do not know. For example, the discovery of dark matter and dark energy has revealed that the atoms we can observe and interact with make up only a small fraction of the universe. Dark matter, which does not emit or absorb light, is thought to make up about 27% of the universe's mass, while dark energy, which is responsible for the accelerated expansion of the universe, makes up roughly 68%. Together, these mysterious substances account for 95% of the universe, leaving only 5% composed of ordinary atoms. Understanding the nature of dark matter and dark energy is one of the greatest challenges in modern physics, and solving this mystery may lead to a deeper understanding of atoms and the universe as a whole. In addition to the mysteries of dark matter and dark energy, there are still unanswered questions about the behavior of atoms on a quantum level. For example, the phenomenon of quantum entanglement, where particles become linked in such a way that the state of one particle is dependent on the state of another, even across vast distances, challenges our understanding of space and time. Einstein famously referred to this as spooky action at a distance, and it remains one of the most puzzling aspects of quantum mechanics. Despite its strangeness, quantum entanglement has been demonstrated experimentally and is being explored for potential applications in quantum computing and secure communication. The study of atoms has also led to practical applications that have transformed our world. In medicine, atomic theory is used in diagnostic techniques such as magnetic resonance imaging, MRI, and positron emission tomography, PET scans. These technologies allow doctors to see inside the human body with incredible detail, helping to diagnose and treat diseases. In energy production, nuclear reactors use controlled atomic fission to generate electricity, providing a significant source of power in many countries. However, the use of atomic energy also comes with significant risks. The accidents at Chernobyl and Fukushima are sobering reminders of the potential dangers of nuclear power. While advances in safety technology have made modern reactors much safer, the issue of radioactive waste disposal remains a major challenge. Finding ways to safely store or neutralize this waste is crucial to the future of nuclear energy. In summary, the study of atoms has transformed our understanding of the universe and our place within it. From the smallest particles to the largest cosmic structures, atoms are the fundamental units of matter and the key to unlocking the mysteries of the natural world. As we continue to explore the behavior of atoms and the forces that govern them, we will undoubtedly uncover new insights that will shape the future of science, technology, and society. The story of atoms is far from over, and the discoveries yet to come will likely be as transformative as those that have come before. The deeper we delve into the nature of atoms, the more their profound role in shaping everything around us becomes evident. The significance of atoms extends far beyond their physical properties, crossing into the realms of philosophy, metaphysics, and even consciousness itself. As scientific understanding evolves, atoms emerge not just as the fundamental particles that make up matter, but as the medium through which the very laws of nature are expressed and understood. One of the key areas where the study of atoms has philosophical implications is the debate between determinism and quantum indeterminacy. In classical physics, atoms and their interactions were thought to follow predictable patterns, governed by fixed laws. However, the advent of quantum mechanics introduced the concept of indeterminacy, most notably through Werner Heisenberg's uncertainty principle. This principle posits that it is impossible to know both the position and the momentum of a particle, like an electron, with absolute certainty. The more precisely one is measured, the less precisely the other can be known. This inherent uncertainty has profound implications for our understanding of reality. In a quantum world, events at the atomic and subatomic levels are not entirely deterministic. They are probabilistic. This challenges the classical Newtonian view that every event in the universe is predetermined by the initial conditions of the atoms involved. Instead, quantum theory suggests that particles, and therefore atoms, exist in a state of probability until observed or measured. This realization has opened up philosophical discussions about the nature of free will, the role of observation in shaping reality, and whether the universe is as predictable as once thought. This probabilistic nature of atomic behavior also leads to the concept of quantum superposition, where particles such as electrons can exist in multiple states simultaneously until they are observed. This phenomenon is famously illustrated by Schrödinger's cat, a thought experiment where a cat in a sealed box is both alive and dead until someone opens the box and observes it. The concept forces us to confront the idea that reality at the atomic level may not align with our everyday experiences. These counterintuitive behaviors highlight the complexities of the quantum world and the challenges it presents to our understanding of reality. The behavior of atoms on the quantum level also brings us into the realm of quantum entanglement. When two particles become entangled, their states become linked in such a way that the state of one particle is directly related to the state of the other, even if they are separated by vast distances. This instantaneous connection seems to defy the speed of light, and has puzzled scientists and philosophers alike. The implications of quantum entanglement are vast, suggesting that at a fundamental level, the universe may be interconnected in ways that we are only beginning to understand. Entanglement has been experimentally verified, and its applications in quantum computing and cryptography could revolutionize technology in ways that are difficult to imagine today. On a broader scale, the study of atoms continues to deepen our understanding of the fundamental forces that shape the universe. Atoms interact through four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. Each of these forces plays a crucial role in the behavior of atoms and the structure of the universe. Gravity, the weakest of the forces on the atomic scale, is the force of attraction between objects with mass. While its effects are negligible at the scale of individual atoms, gravity becomes increasingly significant as we move to larger scales, governing the behavior of planets, stars, and galaxies. The understanding of gravitational forces, stemming from Newton's laws and later refined by Einstein's theory of general relativity, shows us how even atoms contribute to the formation and movement of celestial bodies. Electromagnetism, on the other hand, plays a far more dominant role at the atomic level. This force governs the interactions between charged particles, such as electrons and protons, and is responsible for holding atoms and molecules together. Electromagnetic forces are the reason why chemical bonds form, and they dictate how atoms interact to create the diverse array of substances we observe in the natural world. The electromagnetic spectrum, which includes visible light, radio waves, X-rays, and more, is a result of the interactions between atoms and electromagnetic fields. These interactions give rise to much of the technology we rely on, from wireless communication to medical imaging. The strong nuclear force is perhaps the most powerful of the four forces, binding protons and neutrons together in the atomic nucleus. Despite the repulsive electromagnetic force between positively charged protons, the strong nuclear force holds them tightly within the nucleus, allowing atoms to remain stable. Without this force, the atomic nucleus would fly apart, and matter as we know it would cease to exist. This force is also responsible for the energy released in nuclear reactions, both in the core of stars and in man-made nuclear reactions. The weak nuclear force, although less familiar, is equally important. It governs certain types of particle decay, including the process of beta decay, where a neutron transforms into a proton while emitting an electron and an antineutrino. This process plays a critical role in nuclear reactions within stars and in radioactive decay processes that occur naturally on Earth. The weak nuclear force is essential in the ongoing processes of nuclear fusion in stars, where lighter elements fuse to form heavier ones, powering the stars and creating new elements in the universe. Understanding these fundamental forces and their impact on atoms has allowed scientists to develop the Standard Model of Particle Physics, which provides a framework for explaining the behavior of all known particles and forces, except for gravity, which remains outside the Standard Model. The Standard Model describes the interactions between particles like quarks, gluons, and leptons, which make up protons, neutrons, and electrons, respectively. Although the Standard Model has been incredibly successful in explaining much of what we observe in the universe, it is not yet complete. The search for a theory of everything, one that unifies gravity with the other forces, continues to drive scientific inquiry. Atoms, therefore, are more than just tiny particles that make up matter. They are the nexus through which the forces of nature interact and manifest. Atoms allow us to see the interplay between the laws of physics at the smallest scales, and through them, we can probe the nature of existence itself. For example, the discovery of antimatter, particles that are the opposite of regular matter in terms of charge but otherwise identical, has shown that the universe is far more complex than once thought. Antimatter annihilates matter upon contact, releasing enormous amounts of energy. This raises profound questions. Why is there more matter than antimatter in the universe? What caused this imbalance? The exploration of these mysteries has practical implications as well. Particle accelerators, like the Large Hadron Collider, LHC, smash atoms together at high speeds to study the resulting particles and phenomena. These experiments have led to the discovery of new particles, such as the Higgs boson in 2012, which was crucial in confirming the existence of the Higgs field. This field is responsible for giving particles mass, a fundamental property without which the universe could not exist in its current form. At the same time, the study of atoms extends into our understanding of space and time. Einstein's theory of relativity, which revolutionized our understanding of gravity and space-time, is also linked to the behavior of atoms and light. According to relativity, the mass of an object can influence the curvature of space-time, and thus the path of light. This has been observed in phenomena like gravitational lensing, where light from distant stars is bent around massive objects, allowing us to see objects that would otherwise be hidden. As atoms continue to fuel scientific discoveries, they also challenge our philosophical conceptions of existence. Some physicists and philosophers have proposed that the fundamental nature of reality could be understood in terms of information and computation, where atoms and particles act like bits of data in a vast cosmic computation. This idea, while speculative, has gained traction as quantum computing advances and as the nature of quantum mechanics reveals deeper mysteries about the fabric of reality. This leads to the idea that the universe itself might be a kind of hologram or simulation, where the fundamental code that governs everything from atoms to galaxies is embedded in the very structure of space and time. While this idea remains speculative, it has captivated the imaginations of scientists and laypeople alike, showing just how profound the study of atoms can be. In the practical world, manipulating atoms has allowed for remarkable advancements in technology. Nanotechnology, which operates at the atomic and molecular levels, has revolutionized medicine, materials science, and manufacturing. By controlling the arrangement of atoms, scientists can create materials with extraordinary properties, such as super strength, lightweight structure, or enhanced conductivity. Nanotechnology also holds promise for creating new methods of drug delivery, enabling treatments that can target specific cells in the body with atomic precision. Looking to the future, the study of atoms may unlock new possibilities that we cannot yet fully imagine. As we continue to explore atomic structure, quantum behavior, and the interactions of fundamental particles, we may discover new energy sources, develop faster and more efficient computers, or even uncover deeper truths about the origins of the universe. Atoms are the key to understanding both the universe and our place within it. They reveal the underlying principles that govern all matter and energy, from the simplest elements to the most complex biological systems. The ongoing study of atoms promises to expand our understanding of everything from the smallest particles to the largest cosmic structures, pushing the boundaries of science and technology. As we continue this journey of discovery, the secrets of the atom may unlock new realms of knowledge, enabling us to explore the deepest mysteries of existence itself. The exploration of atoms also serves as a reminder that our understanding of the universe is ever evolving. Throughout history, humanity's conception of the atom has transformed dramatically, from the ancient Greek notion of indivisible particles to the modern understanding of complex subatomic structures governed by quantum mechanics. This ever-changing perspective highlights how scientific inquiry is a continuous process, one that often raises as many questions as it answers. As we expand our knowledge, the atomic world challenges us to reconsider what we know about reality, time, and even life itself. For example, atoms are at the core of the study of chemistry and biology, and through them, we gain insights into the building blocks of life. The very molecules that form DNA, the carrier of genetic information, are made up of atoms arranged in specific patterns. These molecules control the functioning of living organisms, dictating their growth and evolution over time. Without an understanding of atomic and molecular interactions, the field of genetics and the development of modern medicine would be impossible. Consider the role that atoms play in cellular biology, particularly in processes such as metabolism and respiration. The interaction of atoms within molecules like glucose, oxygen, and water is what powers the cells in our bodies. In cellular respiration, atoms are rearranged through chemical reactions to release energy, which is then used to fuel vital processes. The careful balance of these atomic reactions sustains life, and any disruption to this balance can have profound consequences for an organism's health. In medicine, our ability to manipulate atoms and molecules has revolutionized treatments for diseases. The development of pharmaceutical drugs relies on an intricate understanding of how specific atomic arrangements can influence biological processes. Drugs are designed to interact with certain atoms within the body's cells to either inhibit harmful processes or promote healing. This precision in atomic manipulation has enabled the creation of targeted therapies, such as those used in cancer treatments, where specific molecular pathways are targeted to stop the growth of malignant cells while minimizing damage to healthy tissues. Furthermore, the study of atoms has paved the way for advances in diagnostic medicine. Techniques like magnetic resonance imaging, MRI, rely on the behavior of atoms in the presence of magnetic fields. MRI works by detecting the energy released by hydrogen atoms in the body when they are exposed to a strong magnetic field. This allows doctors to visualize internal structures in great detail without the need for invasive procedures. Similarly, nuclear medicine uses radioactive isotopes, atoms with unstable nuclei that emit radiation, to diagnose and treat diseases by tracking how these atoms move through the body or target specific areas. Atoms are also essential to our understanding of environmental science and the challenges we face in preserving the planet's ecosystems. The behavior of atoms in different chemical compounds, such as greenhouse gases, helps scientists understand the processes that drive climate change. Carbon atoms, for example, play a crucial role in the carbon cycle, moving between the atmosphere, oceans, and living organisms. The burning of fossil fuels releases large amounts of carbon dioxide into the atmosphere, where carbon atoms contribute to the greenhouse effect, trapping heat and leading to global warming. By studying the atomic composition of these gases, scientists can better understand the impacts of human activities on the environment and develop strategies to mitigate these effects. Beyond environmental challenges, atoms also help explain the Earth's history. By analyzing the isotopic composition of certain elements in rocks and fossils, scientists can date geological events and uncover the history of life on Earth. Radiometric dating techniques, such as carbon dating, rely on the decay of radioactive isotopes within atoms to estimate the age of ancient objects. This allows us to piece together the timeline of Earth's formation, the evolution of life, and the shifts in climate that have shaped our world. Moreover, atoms allow us to peer even further back in time, to the very origins of the universe itself. The study of atomic nuclei, particularly in stars, provides insight into the processes of nucleosynthesis, where atoms were formed in the hearts of stars through nuclear fusion. In the early moments of the universe, only the lightest elements, hydrogen and helium, existed. As the universe expanded and cooled, stars formed and began fusing these light elements into heavier ones. The carbon, oxygen, nitrogen, and other elements that are essential for life were all forged in the fiery interiors of stars, which later exploded as supernovae, scattering these atoms across the cosmos. This process seeded galaxies, solar systems, and eventually planets like Earth with the elements necessary for the formation of life. Through the lens of atomic science, we gain a deeper appreciation of the interconnectedness of the universe. The atoms that make up our bodies are the same atoms that were forged in ancient stars billions of years ago. This realization brings a profound sense of connection to the cosmos, reminding us that we are quite literally made of stardust. The study of atoms offers a bridge between the microscopic world of quantum particles and the macroscopic world of galaxies, allowing us to understand our place in the grand tapestry of existence. The relationship between atoms and the cosmos is further explored through the field of cosmology. Atoms are key to understanding phenomena such as dark matter and dark energy, which together make up most of the universe's mass energy content. While atoms account for the ordinary matter that we can observe, stars, planets, and galaxies, there is much more in the universe that remains unseen. Dark matter does not interact with light or electromagnetic forces, making it invisible to our current detection methods. However, its gravitational effects on galaxies and clusters of galaxies suggest that it plays a critical role in the structure and evolution of the universe. Similarly, dark energy, a mysterious force driving the accelerated expansion of the universe, may also have connections to the atomic scale, though its true nature remains one of the greatest unsolved mysteries in modern science. These cosmic mysteries underscore the limitations of our current understanding of atoms and the universe. While we have made incredible strides in atomic theory and quantum mechanics, there are still many unanswered questions. For example, the theory of quantum mechanics, which describes the behavior of atoms and particles, is currently incompatible with the theory of general relativity, which describes the behavior of gravity on a large scale. This disconnect presents a challenge for physicists, who are searching for a unified theory that can explain both the atomic and cosmic scales of the universe. One avenue of exploration that may bridge this gap is the study of string theory, which suggests that the fundamental particles that make up atoms are not point-like particles but rather tiny, vibrating strings of energy. According to string theory, different particles arise from different vibrational modes of these strings, and the theory has the potential to unify all the forces of nature, including gravity, in a single framework. While string theory is still largely theoretical and lacks experimental evidence, it represents a bold step toward understanding the true nature of atoms and the universe at the deepest level. Another promising area of research is quantum gravity, which seeks to reconcile quantum mechanics with general relativity. This field aims to develop a theory that describes gravity at the quantum level, potentially shedding light on the nature of black holes, the fabric of spacetime, and the origin of the universe itself. Quantum gravity could also provide insights into phenomena like quantum entanglement and the behavior of particles in extreme conditions, such as those near the event horizon of a black hole. As we continue to push the boundaries of atomic science, it's clear that atoms are not just the building blocks of matter, they are the building blocks of knowledge itself. Each new discovery about the atomic world opens doors to deeper understanding and new possibilities, from advances in technology and medicine to insights into the nature of reality and the cosmos. The study of atoms is a journey that has taken us from the smallest particles to the farthest reaches of the universe, revealing the intricate dance of energy and matter that defines existence. In the coming decades, as new technologies like quantum computing, advanced particle accelerators, and space telescopes come online, we will undoubtedly uncover even more about the nature of atoms. These discoveries will not only deepen our understanding of the universe but will also shape the future of humanity, influencing how we harness energy, develop new materials, and explore the mysteries of consciousness and life itself. In the end, atoms serve as both the foundation of physical reality and the gateway to new realms of understanding. They are the tiniest components of the universe, yet they hold within them the secrets of the stars, the origins of life, and the future of human civilization. As we continue to explore the atomic world, we are reminded that even the smallest things can have the greatest impact, both in science and in the story of existence. Through the study of atoms, we come to see that the universe is not just a collection of particles and forces, but a dynamic, interconnected whole, a vast, ever-changing tapestry woven from the threads of energy, matter, and time. And at the heart of it all, The atom stands as both a symbol of simplicity and the key to unlocking the most profound mysteries of the cosmos. As our understanding of atoms continues to evolve, so too does our ability to manipulate them, and this has profound implications for the future of science and technology. One of the most groundbreaking areas of research is nanotechnology, which operates on the scale of individual atoms and molecules. Nanotechnology allows us to design and create materials and devices at the atomic level, giving us unprecedented control over the physical properties of matter. For instance, nanomaterials can exhibit remarkable strength, conductivity, or chemical reactivity due to the unique arrangements of their atoms. Carbon nanotubes, for example, are composed of carbon atoms arranged in a cylindrical nanostructure, and they possess incredible strength and electrical conductivity, making them promising materials for everything from electronics to structural engineering. Similarly, graphene, a single layer of carbon atoms arranged in a hexagonal lattice, is one of the thinnest and strongest materials known to science, with potential applications in areas ranging from energy storage to advanced computing. Nanotechnology also has transformative potential in the field of medicine. By working at the atomic scale, researchers are developing nanoscale drug delivery systems that can target specific cells or tissues in the body, such as cancer cells, with pinpoint accuracy. These nanodevices can be designed to release drugs in response to specific stimuli, such as changes in pH or temperature, ensuring that the treatment is delivered only where it is needed and minimizing side effects. Additionally, nanotechnology holds promise for creating artificial tissues, organs, and even nanoscale robots, known as nanobots, which could one day perform precise medical procedures within the human body, repairing damaged tissues or attacking pathogens at the atomic level. The implications of nanotechnology extend far beyond medicine. In the energy sector, scientists are exploring the use of nanomaterials to create more efficient solar cells, batteries, and fuel cells. By manipulating the arrangement of atoms and materials, they aim to improve the conversion of sunlight into electricity, enhance energy storage capacity, and increase the efficiency of chemical reactions involved in energy production. This could lead to significant advancements in renewable energy technologies, helping to address the global challenge of climate change. Moreover, nanotechnology is pushing the boundaries of what is possible in computing. Traditional computers rely on the movement of electrons through semiconductor materials, but as we approach the limits of miniaturization in current chip designs, the need for new technologies becomes evident. Quantum computing, which operates at the atomic and subatomic level, offers the potential to revolutionize computation by harnessing the strange behavior of quantum particles. In a quantum computer, bits of information, known as qubits, can exist in multiple states simultaneously, thanks to the phenomenon of superposition. This allows quantum computers to process vast amounts of information at once, solving problems that would be impossible for classical computers. Quantum computing is still in its early stages, but its potential applications are staggering. It could be used to model complex molecular interactions, accelerating drug discovery and materials science research. It could also enable more efficient encryption methods, revolutionizing cybersecurity. However, building a functional quantum computer requires an intricate understanding of atomic behavior, as quantum systems are highly sensitive to their environment and must be kept in a state of coherence to function properly. Another frontier in atomic research is the study of fusion energy, which promises to provide a nearly limitless, clean energy source by replicating the processes that power the sun. Fusion occurs when atomic nuclei are forced together at high temperatures and pressures, releasing a tremendous amount of energy. Unlike nuclear fission, which splits heavy atoms and produces radioactive waste, fusion uses light atoms like hydrogen, and its primary byproduct is harmless helium. However, achieving the conditions necessary for sustained fusion on Earth has proven to be a formidable challenge. Recent advances in magnetic confinement techniques, such as those used in tokamak reactors, and breakthroughs in laser-induced inertial confinement have brought us closer to realizing practical fusion power. If successful, fusion could revolutionize the energy industry, providing a sustainable alternative to fossil fuels and reducing humanity's carbon footprint. The dream of harnessing atomic energy for the benefit of all humankind, without the dangers associated with current nuclear technology, may soon become a reality. The study of atoms also raises profound questions about the nature of reality itself. As we delve deeper into the atomic and subatomic realms, we encounter phenomena that defy our everyday understanding of the world. Quantum mechanics, the branch of physics that describes the behavior of particles at the atomic scale, reveals a universe where particles can exist in multiple states at once, communicate instantaneously across vast distances, and behave unpredictably until observed. These bizarre behaviors challenge our classical notions of cause and effect, determinism, and the flow of time. One of the most famous examples of quantum weirdness is the double-slit experiment, in which particles such as electrons behave like waves, creating an interference pattern when passed through two slits. However, when observed, the particles revert to behaving like solid objects, with the interference pattern disappearing. This experiment illustrates the concept of wave-particle duality and suggests that the act of observation fundamentally alters the behavior of quantum systems. It raises the question of whether reality exists independently of our observations or whether consciousness plays an active role in shaping the physical world. Quantum entanglement is another puzzling phenomenon in which two particles become linked in such a way that the state of one particle instantaneously influences the state of the other, regardless of the distance between them. This spooky action at a distance, as Einstein famously called it, has been experimentally verified and is being explored for applications in quantum communication and cryptography. However, the implications of entanglement challenge our understanding of space, time, and causality, suggesting that the fabric of reality may be far more interconnected than we can currently comprehend. These insights from quantum mechanics have led some physicists and philosophers to question the very nature of existence. If reality at the atomic level is governed by probabilities and uncertainties, does this mean that determinism is an illusion? Does free will arise from the randomness inherent in quantum processes? Or are there hidden variables that we have yet to discover, which would restore order to the apparent chaos of the quantum world? As we ponder these questions, it becomes clear that the study of atoms is not just about understanding the physical structure of matter but also about exploring the fundamental nature of existence. Atoms are the building blocks of everything we see, but they are also the doorway to mysteries that transcend our current understanding. The atomic world invites us to rethink our assumptions about reality, challenging us to expand our minds and embrace the unknown. In the future, as we continue to explore the atomic and subatomic realms, we may discover new laws of physics, uncover hidden dimensions, or even encounter evidence of parallel universes. The possibilities are as vast and mysterious as the universe itself. Whether we are studying the behavior of individual atoms or the quantum foam at the edge of spacetime, the pursuit of atomic knowledge will undoubtedly lead to new breakthroughs that reshape our understanding of the world and our place within it. The journey of atomic exploration is far from over. From the ancient philosophers who first speculated about the existence of atoms to the modern scientists who manipulate them with incredible precision, humanity has been on a quest to unlock the secrets of the smallest components of the universe. Along the way, we have made astonishing discoveries, developed life-changing technologies, and expanded the frontiers of knowledge. But the deeper we go, the more we realize how much we have yet to learn. Atoms are more than just the building blocks of matter. They are the key to understanding the universe, life, and reality itself. Each discovery about atoms brings us one step closer to answering the big questions. Where did we come from? What is the nature of existence? What is the future of the universe? As we continue to explore the atomic world, we are reminded that even the smallest things can contain the greatest mysteries, and that within the atom lies the potential to unlock the deepest truths of the cosmos. As we delve deeper into the atomic world, we also encounter the profound implications that atomic theory has on our understanding of time and space. While atoms are fundamental to matter, their behavior on a quantum level challenges our classical perceptions of these concepts. The intricate relationship between atoms and the very fabric of spacetime is one of the most fascinating areas of modern physics, as it invites us to reconsider the linear and absolute nature of time, as well as the rigidity of space. Quantum mechanics, particularly through experiments involving subatomic particles, demonstrates that time and space are not as straightforward as we once thought. At the quantum level, particles can tunnel through barriers, existing in one place at one moment and suddenly appearing in another, seemingly bypassing the traditional constraints of time and space. This phenomenon, known as quantum tunneling, is not merely theoretical. It has been experimentally verified and is applied in technologies such as scanning tunneling microscopes, which allows scientists to observe atomic-scale features. Beyond the immediate applications, the implications of quantum tunneling stretch into philosophical and existential domains. If atoms, which make up all of reality, can seemingly bypass physical barriers, then what does this suggest about the underlying structure of the universe? Is space-time itself flexible, or is there an even more fundamental layer of reality that governs how atoms and particles behave? Moreover, quantum entanglement, where two particles remain connected regardless of the distance between them, further complicates our understanding of space. When two entangled particles are separated by vast distances, any change in one particle's state is instantaneously reflected in the other, suggesting that information can travel faster than the speed of light, or that the very notion of distance becomes irrelevant at the quantum level. This phenomenon, deeply intertwined with atomic behavior, challenges one of the bedrock principles of classical physics, Einstein's theory of relativity, which holds that nothing can travel faster than light. These ideas have prompted researchers to investigate the potential link between quantum mechanics and the theory of relativity, particularly through the lens of quantum gravity. If atoms and subatomic particles can exhibit such bizarre, non-local behaviors, then the laws of gravity, understood through general relativity, might need to be reimagined at these tiny scales. The search for a unified theory that can reconcile the behavior of atoms and subatomic particles with the cosmic scale forces of gravity is a quest that continues to drive theoretical physics today. One promising avenue in this search is string theory, which posits that the fundamental building blocks of reality are not particles, but rather tiny, vibrating strings of energy. According to string theory, the different vibrational modes of these strings give rise to all known particles, including the atoms that form matter. While still highly theoretical and lacking in direct experimental evidence, string theory has the potential to unify the forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces, under a single framework. This unification would offer profound insights into how atoms and particles interact not just with each other, but with the very structure of space-time. In the context of string theory, the atoms that make up our bodies and the universe are viewed as manifestations of vibrating strings that exist in a multidimensional space. These dimensions are not limited to the familiar three dimensions of space and one of time, but may include many additional dimensions that are curled up or hidden from our perception. If true, this would suggest that the atoms and particles we observe are only a fraction of the full reality, and that the atomic world is far more complex than we can currently comprehend. The potential existence of extra dimensions also opens up the possibility of parallel universes, each with its own unique arrangement of atoms and particles. In this view, the atoms that make up our universe could be part of a much larger multiverse, with countless other universes existing alongside our own. These ideas, once confined to the realm of science fiction, are now serious subjects of scientific inquiry, driven by the strange and unexpected behavior of atoms and particles at the quantum level. Beyond the realm of theoretical physics, atoms play a crucial role in our quest to understand the ultimate fate of the universe. The study of atomic interactions provides insight into the forces driving the expansion of the universe and the mysterious dark matter and dark energy that dominate the cosmos. While atoms make up the visible matter in the universe, accounting for stars, planets, and galaxies, this visible matter constitutes only a small fraction of the universe's total mass and energy. The vast majority of the universe is made up of dark matter, which interacts with visible matter through gravity, and dark energy, which is driving the accelerated expansion of the universe. The connection between atoms and the fate of the universe underscores a fundamental truth. The atomic world is not isolated from the grand scale of cosmic events, but is intricately woven into the fabric of existence. The same atoms that constitute the stars, galaxies, and distant nebulae are the ones that make up our bodies, linking us directly to the cosmos. This idea, sometimes called cosmic connectedness, is beautifully expressed in the famous phrase, "We are made of star stuff." Every atom in our bodies was forged in the heart of a dying star, and through the process of stellar nucleosynthesis, those atoms were scattered across space in supernova explosions, eventually coalescing into new stars, planets, and life forms. In this sense, the study of atoms is also a study of our origins. Tracing the journey of atoms from the Big Bang to the formation of life on Earth provides a deeper understanding of how life emerged from the seemingly chaotic and random interactions of particles and forces. The atoms in the hydrogen and oxygen molecules that make up water, for instance, have existed since the earliest moments of the universe. The carbon atoms that form the backbone of organic molecules, the molecules essential to life, were forged in the intense heat and pressure of dying stars. The iron in our blood, the calcium in our bones, the nitrogen in our DNA, all of these elements were created in the nuclear furnaces of stars billions of years ago. This profound realization has not only influenced scientific thought but also shaped our philosophical and spiritual perspectives on life. The fact that atoms, once part of ancient stars, now make up the human body connects us to the vast history of the universe. In this way, the study of atoms provides a cosmic perspective on our place in the universe, reminding us that we are part of something much larger than ourselves. As we continue to explore the atomic world, we are also reminded of the limitations of our knowledge. Despite centuries of scientific progress, there is still much we do not understand about atoms, especially when it comes to their interactions with the forces of nature. The mysteries of dark matter and dark energy, for example, remain largely unsolved, and we have only scratched the surface of understanding the true nature of quantum mechanics. These mysteries drive ongoing research and experimentation, as scientists work to unlock the secrets of the atomic and subatomic realms. In recent years, new technologies have emerged that allow us to probe atoms in ways that were once thought impossible. One such technology is the Large Hadron Collider, LHC, a particle accelerator that can smash atoms and subatomic particles together at incredibly high energies. By studying the resulting particle collisions, scientists have made groundbreaking discoveries, including the detection of the Higgs boson, a fundamental particle that plays a crucial role in giving other particles their mass. The discovery of the Higgs boson confirmed the existence of the Higgs field, an invisible field that permeates all of space and interacts with certain particles, slowing them down and endowing them with mass. This discovery was a major milestone in the field of particle physics and provided key insights into how atoms and their constituent particles acquired the properties we observe. The LHC and other particle accelerators are also helping scientists explore new frontiers in physics, such as the search for supersymmetry and extra dimensions. Supersymmetry, a theoretical framework that suggests every known particle has a heavier, superpartner particle, could provide answers to some of the biggest questions in physics, including the nature of dark matter. While supersymmetric particles have yet to be discovered, experiments at the LHC are bringing us closer to either confirming or ruling out this theory, which could reshape our understanding of the atomic world. Another exciting area of atomic research is the development of new materials through the manipulation of atomic and molecular structures. Advances in material science are allowing us to design substances with specific properties tailored to various applications. For example, researchers are exploring ways to create superconductors that can operate at room temperature, a breakthrough that would revolutionize energy transmission and storage by allowing electricity to flow without resistance. Currently, superconductors must be cooled to extremely low temperatures to function, but finding a way to create high-temperature superconductors would have enormous practical benefits, from more efficient power grids to faster and more powerful computers. The ability to manipulate atoms with precision has also given rise to the field of synthetic biology, where scientists are designing and creating new forms of life at the molecular level. By re-engineering the DNA of organisms, researchers can develop bacteria that produce biofuels, plants that are resistant to pests, and even synthetic cells that perform specific tasks, such as cleaning up environmental pollutants. This merging of atomic science with biology has the potential to revolutionize medicine, agriculture, and industry, ushering in a new era of innovation. However, with these advancements come ethical considerations. As we gain more control over atoms and the building blocks of life, we must grapple with the potential consequences of our actions. The ability to create new materials, life forms, and technologies at the atomic level raises questions about safety, environmental impact, and the potential for misuse. For example, the development of advanced nanotechnology could lead to powerful new weapons, or the unchecked manipulation of DNA could have unforeseen consequences for ecosystems and human health. These concerns highlight the need for responsible research and the establishment of ethical guidelines to ensure that atomic science is used for the benefit of humanity and not for harm. The atomic world, while offering incredible potential, also reminds us of the delicate balance that exists in nature. Atoms are stable because of the forces that hold them together, but when those forces are disrupted, such as in a nuclear explosion, the results can be catastrophic. The power contained within atoms is immense, as evidenced by the development of nuclear weapons, which release energy through the splitting, fission, or combining, fusion, of atomic nuclei. The destructive power of these weapons is a sobering reminder of the dual nature of atomic science. It can be used to create and innovate, but it can also destroy. In the face of such power, humanity has a responsibility to harness atomic science for peaceful and constructive purposes. The development of nuclear energy, for example, offers a way to generate electricity without the harmful emissions associated with fossil fuels. By tapping into the energy released during nuclear fission, nuclear power plants can provide a steady and reliable source of electricity. However, concerns about safety, waste disposal, and the potential for nuclear proliferation have prompted debates about the future of nuclear energy. As we continue to explore the atomic world, finding ways to safely and sustainably harness atomic energy will be a key challenge for future generations. Ultimately, the study of atoms is a journey into the heart of matter, revealing the forces and particles that make up everything in the universe. From the smallest subatomic particles to the largest structures in the cosmos, atoms are the building blocks of reality, and their study has the potential to unlock the deepest mysteries of existence. As we continue to explore and manipulate the atomic world, we must do so with humility, responsibility, and a sense of wonder for the incredible complexity and beauty of the universe at every scale. As we continue to explore the atomic world, we uncover not just the foundation of matter, but also the vast interconnectedness of the physical laws governing the universe. Atoms, in their simplicity, are deceptively complex, embodying the intricate relationships between the fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces. These forces, in turn, dictate how atoms form, bond, and react with one another, shaping everything from the smallest molecules to the largest cosmic structures. One of the most striking manifestations of this atomic complexity is the process of chemical bonding. Atoms rarely exist in isolation. Instead, they interact with other atoms to form molecules, creating the diversity of substances and materials that make up the physical world. The manner in which atoms bond depends on the number of electrons in their outermost shell, and these interactions are governed by the principles of quantum mechanics. Electrons exist in probabilistic clouds, or orbitals around the nucleus, and their behavior cannot be predicted with certainty. Only the probability of finding an electron in a certain region can be calculated. When atoms bond to form molecules, they can do so in a variety of ways, including covalent bonding, ionic bonding, and metallic bonding. In covalent bonds, atoms share electrons, creating stable, strong connections that hold molecules together. This type of bonding is responsible for the structure of most organic molecules, including the DNA in our cells. Ionic bonds, on the other hand, involve the transfer of electrons from one atom to another, resulting in the formation of positively and negatively charged ions. These opposite charges attract, creating a bond. Ionic bonding is crucial in the formation of salts, such as sodium chloride, table salt. Metallic bonding, characteristic of metals, occurs when electrons are shared and delocalized across many atoms, allowing for the unique properties of metals, such as conductivity and malleability. The diversity of bonding possibilities gives rise to the vast array of materials and substances found in nature. From the hardness of diamonds, composed of carbon atoms in a crystalline covalent network, to the flexibility of rubber, made from long chains of carbon and hydrogen atoms, the behavior of atoms at the molecular level determines the properties of matter. Scientists have harnessed this understanding to develop new materials with tailored properties, such as graphene, a single layer of carbon atoms arranged in a hexagonal lattice. Graphene's remarkable strength, flexibility, and electrical conductivity hold promise for a wide range of applications, from advanced electronics to stronger, lighter materials for aerospace. At an even more fundamental level, the forces that govern atomic behavior also shape the larger structures in the universe. The electromagnetic force, responsible for the interactions between charged particles, is critical for the formation of atoms and molecules. This force keeps electrons bound to the nucleus, while also dictating the interactions between different atoms that result in chemical bonding. Without the electromagnetic force, matter as we know it would not exist. However, the strong nuclear force, which operates at the subatomic level, is perhaps the most essential for the existence of atoms themselves. This force binds protons and neutrons together in the nucleus, overcoming the repulsive electromagnetic force between the positively charged protons. The strong nuclear force is incredibly powerful but operates only over extremely short distances, within the nucleus of an atom. Without it, atomic nuclei would fly apart, and atoms could not exist. While the strong nuclear force holds nuclei together, the weak nuclear force plays a crucial role in radioactive decay and nuclear reactions. This force is responsible for processes such as beta decay, in which a neutron in the nucleus decays into a proton, an electron, and a neutrino. Beta decay is vital for the transformation of elements over time, influencing the behavior of atoms in nuclear reactors and the life cycle of stars. The interplay between these fundamental forces not only allows for the existence of atoms, but also drives the processes that power the stars. Inside the cores of stars, including our Sun, nuclear fusion occurs, where atoms are smashed together under extreme pressure and temperature to form heavier elements. In the Sun, hydrogen atoms fuse to form helium, releasing vast amounts of energy in the process. This energy is what powers the Sun and, by extension, life on Earth. The fusion of heavier elements occurs in larger stars, which produce elements such as carbon, oxygen, and iron before they die in spectacular supernova explosions. It is through this stellar nucleosynthesis that the heavier elements essential to life are created and distributed throughout the cosmos. As stars undergo nuclear fusion, they act as atomic forges, constantly converting simple atoms into more complex ones. This process plays a critical role in the cosmic cycle of matter. When massive stars explode as supernovae, they scatter the elements they have created into space, seeding future generations of stars and planets. The atoms that make up Earth, and every living organism on it, were once part of these distant stars. This recycling of atoms across space and time is a constant reminder of the interconnectedness of all matter in the universe. But as stars give birth to new elements, they also bring about the eventual end of their own existence. When a star exhausts its nuclear fuel, its fate depends on its mass. Smaller stars, like our Sun, will shed their outer layers and form dense remnants known as white dwarfs. Larger stars, however, may undergo a gravitational collapse, forming either a neutron star or a black hole, where matter is crushed to an extraordinary density. These extreme cosmic objects offer a glimpse into the boundaries of atomic and subatomic behavior under conditions of immense gravity and pressure, challenging our understanding of physics. On Earth, the study of atomic behavior has led to the development of technologies that harness the energy locked within atoms. Nuclear fission, the splitting of atomic nuclei, is the process that powers nuclear reactors and nuclear weapons. In nuclear power plants, atoms of uranium or plutonium are split, releasing energy that is used to generate electricity. However, this same process, when used in nuclear weapons, unleashes devastating amounts of energy in the form of explosions. The potential of nuclear energy is immense, but it also raises significant ethical and environmental questions. The detonation of nuclear weapons in warfare has had catastrophic consequences, and the prospect of nuclear proliferation continues to pose a threat to global security. At the same time, nuclear power presents a low-carbon alternative to fossil fuels, offering a potential solution to the challenge of climate change. However, the risks associated with nuclear accidents, such as the disasters at Chernobyl and Fukushima, as well as the challenge of managing radioactive waste, make the future of nuclear energy a subject of ongoing debate. Another area of atomic research that holds great promise is nuclear fusion, the process that powers stars. Unlike fission, which splits heavy atomic nuclei, fusion involves the combination of light nuclei, such as hydrogen, to form heavier elements and release energy. Fusion has the potential to provide a nearly limitless source of energy, as the fuel required for fusion, isotopes of hydrogen, are abundant on Earth. Moreover, fusion does not produce long-lived radioactive waste or pose the same risks of meltdown as fission reactors. However, achieving controlled nuclear fusion on Earth has proven to be an immense scientific and engineering challenge. While experimental fusion reactors, such as the International Thermonuclear Experimental Reactor, ITER, are making progress, practical fusion power remains a goal for the future. The pursuit of fusion energy reflects humanity's desire to harness the power of the atomic world for the betterment of society. Yet, as we continue to explore the atomic realm, we are constantly reminded of its inherent duality, the capacity for both creation and destruction. Atoms are not just the building blocks of matter, they are also the source of immense energy, both constructive and destructive. This duality is evident not only in nuclear power but also in the everyday use of atomic science, from medical treatments using radiation to the development of new materials and technologies. In the future, our understanding of atoms and their behavior will likely lead to even more revolutionary discoveries and applications. Quantum computing, for instance, promises to transform the way we process information by leveraging the strange properties of subatomic particles, such as superposition and entanglement, to perform complex calculations far faster than classical computers. These advancements could unlock new solutions to problems in fields ranging from cryptography to artificial intelligence to drug discovery. In addition to technological advancements, the continued study of atoms will deepen our understanding of the universe itself. By probing the behavior of subatomic particles at higher energies and smaller scales, physicists hope to uncover new insights into the nature of matter, energy, and the forces that govern them. This research could lead to a greater understanding of the early moments of the universe, the behavior of black holes, and the unification of quantum mechanics with the theory of general relativity. In the end, the study of atoms is a never-ending journey into the very heart of existence. Each discovery opens new doors to understanding the universe, from the smallest particles to the largest structures. As we continue to unravel the mysteries of the atomic world, we gain not only a deeper appreciation of the physical universe but also a greater sense of our place within it. The atoms that make up everything around us, our bodies, our planet, and the stars in the sky, are the same atoms that have existed since the dawn of time, forever cycling through the cosmos. Through the study of atoms, we come to realize that we are, in every sense, part of the grand tapestry of the universe, woven together by the fundamental forces that govern all matter. As we venture deeper into the exploration of atoms, we are not only tracing the past of the universe but also peering into its potential future. The study of atoms brings with it the tantalizing question: what lies ahead for the universe, for matter, and for life itself? The same atoms that have been integral to the formation of stars and galaxies, the same atoms that make up the fabric of our bodies, hold within them the answers to some of the biggest questions that science has yet to resolve. One of the most fundamental questions in the realm of atomic science is tied to the fate of the universe. The universe, ever since the Big Bang, has been expanding. This discovery, made in the early 20th century, revolutionized our understanding of cosmology. But as we look toward the future, questions about the universe's ultimate destiny become even more complex. At the core of these questions is the mysterious phenomenon of dark energy, an unknown force that appears to be driving the acceleration of the universe's expansion. Dark energy is not composed of atoms or any familiar particles of matter. In fact, it does not interact with atoms in the way we expect forces to behave. It is this elusive, almost invisible presence in the universe that dominates its total energy content, making up about 68% of the cosmos, yet its nature remains one of the biggest mysteries in modern science. Understanding dark energy could shed light on the future of the atomic world. Will the universe continue to expand forever, with galaxies drifting farther apart, eventually leaving only isolated atoms in a cold, dark void? Or will the expansion reverse, leading to a big crunch, where all matter is pulled back into a singularity, collapsing the very atoms that once formed stars and galaxies? The fate of the universe is intricately tied to the behavior of atoms, especially as we explore the possibility of atomic decay. On incredibly long timescales, even the most stable atoms may not last forever. Protons, for example, are considered one of the most stable particles, but some theories suggest that they too could eventually decay, albeit over timescales far longer than the current age of the universe. If protons decay, it would mean that matter, as we know it, would gradually disintegrate over time. The atoms that make up stars, planets, and even life itself could one day fade into a sea of subatomic particles. This process, known as proton decay, remains a hypothetical concept, but it touches on the fragility of matter in the grand scheme of the cosmos. Beyond the speculative future of proton decay, we also face more immediate questions about the atomic structure of matter at its most fundamental levels. The world of particle physics has already revealed a complex zoo of subatomic particles beyond the familiar protons, neutrons, and electrons that make up atoms. Quarks, neutrinos, muons, and other exotic particles play vital roles in the stability and interactions of atoms. Yet, there may still be particles and forces that have yet to be discovered. The standard model of particle physics, which describes the behavior of these particles, has proven remarkably successful, but it is far from complete. It does not account for dark matter or dark energy, and it fails to explain gravity at the quantum level. These gaps point toward a deeper theory, potentially one that unifies all the fundamental forces of nature, including gravity, into a single framework, a theory of everything. The quest for a theory of everything brings us to the cutting edge of atomic science, quantum gravity. Current theories, such as string theory, propose that at the smallest scales, even atoms and subatomic particles are not solid objects but rather vibrating strings of energy. These strings, far smaller than the protons and neutrons in an atom's nucleus, could provide the key to understanding how gravity operates on quantum scales, uniting it with the other forces of nature. If proven correct, string theory or similar frameworks could revolutionize our understanding of atoms, particles, and the very fabric of space-time. However, string theory is just one possibility. Other approaches, such as loop quantum gravity, offer different insights into how gravity and quantum mechanics might interact. These theories propose that space-time itself is quantized, meaning that at the smallest scales, it is composed of discrete, indivisible units, much like atoms are the building blocks of matter. This view suggests that the very structure of reality might be granular, challenging our understanding of continuity and space. Discovering the true nature of quantum gravity could unlock profound new knowledge about the behavior of atoms under extreme conditions, such as those found near black holes or during the earliest moments of the universe. Speaking of black holes, they present another deep connection between atomic behavior and the larger structure of the cosmos. Black holes are regions of spacetime where gravity is so intense that not even light can escape. At their cores, matter is compressed to infinite density, and the known laws of physics break down. This singularity, where atoms and particles are crushed beyond recognition, raises fundamental questions about the limits of atomic structure. What happens to atoms as they approach a black hole's event horizon? Do they disintegrate into their constituent particles, or does some unknown physics come into play? The study of black holes, particularly through the lens of atomic and particle physics, has the potential to reshape our understanding of both the very large and the very small. One of the most exciting developments in this area is the detection of gravitational waves, ripples in spacetime caused by the acceleration of massive objects, such as merging black holes or neutron stars. These waves, first directly detected in 2015, have opened a new window into the study of the universe. By observing the effects of gravitational waves on atomic particles, scientists can explore phenomena that were previously beyond the reach of traditional telescopes. These waves allow us to probe the interactions of matter and energy in the most extreme environments, providing new insights into the behavior of atoms and particles under conditions of intense gravity. But while the study of black holes and gravitational waves pushes the boundaries of atomic science, there are other, more tangible applications of atomic knowledge that continue to transform society. The discovery of radioactivity in the late 19th century revolutionized our understanding of atomic structure and led to significant advancements in medicine, energy, and industry. Today, radioactive isotopes are used in medical imaging and cancer treatment, allowing doctors to diagnose and treat diseases with unprecedented precision. Atomic science has had a profound impact on our ability to harness energy. Nuclear power, as previously discussed, provides a low-carbon source of energy that could play a key role in addressing the global challenge of climate change. However, the safe and responsible use of nuclear energy remains a critical issue. Advances in reactor design, such as the development of thorium reactors and small modular reactors, offer the potential for safer, more efficient nuclear power. These reactors use different types of fuel and are designed to reduce the risk of meltdowns and minimize the production of long-lived radioactive waste. As the world transitions to cleaner sources of energy, the role of atomic science in shaping the future of energy production will be pivotal. Moreover, the manipulation of atoms at the nanoscale has given rise to the field of nanotechnology, which is revolutionizing industries from electronics to materials science. Nanotechnology involves the precise control of matter at the atomic and molecular levels, allowing for the creation of materials with unique properties. For example, nanoparticles can be engineered to have specific electrical, optical, or chemical characteristics, leading to innovations in everything from solar cells to drug delivery systems. The ability to manipulate atoms in such a precise manner opens up a world of possibilities, from the development of new materials with enhanced strength and durability to the creation of nanobots capable of performing tasks inside the human body. As we advance our ability to control atoms and their interactions, we also face the ethical challenges that come with such power. The potential for misuse of atomic science, whether through the proliferation of nuclear weapons or the unintended consequences of genetic engineering, requires careful consideration and regulation. The duality of atomic science, its capacity to both create and destroy, remains a central theme as we move forward into the atomic age. How we choose to wield this power will determine the future of humanity and the planet. In conclusion, the study of atoms is far more than a journey into the subatomic world. It is a quest to understand the very nature of reality. From the ancient Greek philosophers who first speculated about the existence of indivisible particles to the modern-day physicists unraveling the mysteries of quantum mechanics, our exploration of atoms has expanded the boundaries of human knowledge in profound ways. Atoms are the building blocks of all matter, but they are also gateways to understanding the universe's most fundamental forces and phenomena. As we continue to push the limits of atomic science, we are not only uncovering the secrets of matter but also gaining deeper insights into the origins, structure, and future of the cosmos. The story of atoms is the story of the universe itself, a story that is still unfolding, with new discoveries waiting to be made. As we continue our exploration of the atom, we realize that its relevance extends beyond the scientific and technological realms into philosophical and existential questions about life and the universe. In understanding atoms, we delve into the very fabric of existence, addressing questions about where we come from, what we are made of, and what the ultimate fate of everything might be. Atoms have an intrinsic role in shaping these inquiries because they represent the most fundamental building blocks of the universe. Yet, they also reveal profound mysteries that compel us to rethink our place in the cosmos. One fascinating aspect of atomic science is the connection between atoms and the origins of life. While atoms themselves are inanimate, the way they bond together to form molecules underpins all biological processes. Life as we know it is fundamentally a result of atoms assembling into more complex structures. The carbon atom, in particular, plays an unparalleled role in biology. Carbon's ability to form long, stable chains and rings, combined with its tendency to bond with many other elements, makes it the backbone of all known life forms. The versatility of carbon atoms allows for the formation of complex molecules like proteins, DNA, and lipids, which are essential for cellular function. The understanding of atoms has significantly advanced the field of biochemistry, shedding light on how the molecules of life function. Each biological process, from metabolism to replication, involves the interaction of atoms within larger molecules. Enzymes, which catalyze biochemical reactions, owe their function to the specific arrangement of atoms in their active sites. Similarly, DNA replication depends on the precise pairing of atoms in nucleotide bases. Even small changes in atomic structure, such as the replacement of one atom with another in a protein, can lead to dramatic changes in biological function, sometimes resulting in diseases or advantageous traits. Atoms are not only responsible for the processes that sustain life but also for its very origin. The question of how life began on Earth is one of the most compelling mysteries in science. The most widely accepted theory is that life arose from a primordial soup of atoms and simple molecules that, under the right conditions, formed the first self-replicating systems. This theory, known as abiogenesis, proposes that the early Earth provided an environment rich in the necessary ingredients, atoms of carbon, hydrogen, oxygen, nitrogen, and other elements, along with the energy needed to drive chemical reactions. These atoms gradually formed increasingly complex molecules, eventually leading to the first living organisms. While the details of how life first emerged remain elusive, atomic science provides a framework for understanding the conditions that might have led to this profound event. By studying how atoms and molecules behave under various conditions, scientists can simulate the early Earth environment and test hypotheses about the origins of life. Furthermore, the search for life beyond Earth, astrobiology, depends heavily on understanding atoms. When scientists search for signs of life on other planets or moons, they look for the same basic atomic ingredients that are essential for life on Earth: water, H2O, carbon-based molecules, and energy sources capable of driving chemical reactions. The search for extraterrestrial life is not just about finding alien creatures. It's about uncovering whether the conditions that allowed atoms to come together to form life on Earth are unique or common throughout the universe. Mars, Europa, one of Jupiter's moons, and Enceladus, one of Saturn's moons, are all promising candidates in this search because they are believed to have water and organic molecules, key atomic ingredients for life. The discovery of life elsewhere in the universe would be one of the most significant scientific discoveries of all time, fundamentally altering our understanding of atoms' role in the cosmos and potentially revealing new forms of chemistry that could exist under alien conditions. Moreover, the study of atoms also provides insight into the possibility of creating artificial life. With the advent of synthetic biology, scientists are now able to manipulate atoms within DNA and other biomolecules to design new organisms. These organisms may have practical applications, such as producing biofuels, cleaning up environmental pollutants, or manufacturing pharmaceuticals. The manipulation of atoms in this context not only allows us to understand life better but also to engineer it for specific purposes. However, this raises ethical questions about how far we should go in manipulating life at the atomic level. As we gain more control over the building blocks of life, we must carefully consider the potential consequences of these actions. As we dive further into the atomic world, we also confront questions about the future of human life. The same atoms that form the basis of biological processes might one day be manipulated to extend life, enhance cognitive function, or even interface with machines. Advances in nanotechnology and molecular engineering hold the potential to revolutionize medicine and human health. By controlling atoms at the nanoscale, scientists are developing new treatments that can target diseases with unprecedented precision. Nanoparticles can be designed to deliver drugs directly to cancer cells, minimizing side effects and improving treatment efficacy. Similarly, researchers are exploring ways to use atomic-scale technologies to repair damaged tissues, regenerate organs, or even slow down the aging process. The field of atom-based technology is also advancing in ways that could transform how we interact with the world around us. Quantum computing, which leverages the strange behaviors of atoms and subatomic particles, promises to revolutionize industries ranging from cryptography to materials science. Unlike classical computers, which use bits that represent either a 0 or a 1, quantum computers use quantum bits, or qubits, which can represent both 0 and 1 simultaneously thanks to a phenomenon known as superposition. This allows quantum computers to perform complex calculations much faster than traditional computers, potentially solving problems that are currently intractable. The power of quantum computing lies in the manipulation of individual atoms and particles, which behave in ways that defy classical physics. For instance, quantum entanglement allows particles to become linked in such a way that the state of one particle is dependent on the state of another, no matter how far apart they are. This phenomenon, which Einstein famously referred to as spooky action at a distance, could one day be used to create ultra-secure communication systems that are immune to hacking. Quantum computers could also lead to breakthroughs in materials science, as they have the potential to simulate atomic interactions in ways that are currently impossible, leading to the design of new materials with novel properties. However, as we venture further into the realm of quantum mechanics and atomic manipulation, we also encounter profound philosophical questions. Atoms, which were once thought to be indivisible and the smallest units of matter, are now known to be composed of even smaller particles, quarks, leptons, and bosons. These particles obey the strange rules of quantum mechanics, where probability replaces certainty, and particles can exist in multiple states simultaneously. This quantum world challenges our classical understanding of reality, leading to questions about the nature of existence itself. How can particles be in two places at once? How do we reconcile the deterministic laws of classical physics with the probabilistic nature of quantum mechanics? One of the most famous thought experiments in quantum mechanics is Schrödinger's cat, which illustrates the paradox of quantum superposition. In this scenario, a cat in a box is simultaneously both alive and dead until an observer opens the box and measures its state. This thought experiment highlights the strange and counterintuitive nature of quantum mechanics, where the act of observation seems to determine the outcome of an event. The implications of this for our understanding of reality are profound. Does reality exist independently of observation, or do we play an active role in shaping it? The study of atoms, which are governed by quantum mechanics, forces us to confront these deep philosophical questions. At its core, the exploration of atoms is about much more than understanding the physical world. It is about probing the fundamental nature of reality, the origins of life, and the future of human civilization. Atoms are not just the building blocks of matter, they are the foundation of everything we see, touch, and experience. As we continue to unravel their mysteries, we are reminded that the smallest things in the universe often hold the greatest secrets. From the origins of life to the fate of the universe, atoms are at the heart of some of the most profound questions we can ask. And as our understanding of atoms grows, so too does our appreciation for the complexity and beauty of the universe they form. In conclusion, atoms, though seemingly simple, are the key to unlocking the deepest mysteries of existence. Their study has not only transformed our understanding of the natural world but has also opened new horizons for exploration and discovery. As we look to the future, the atom will continue to be a source of wonder and inspiration, driving us to ask bigger questions and seek even greater answers. Whether in the context of cosmology, biology, technology, or philosophy, the atom remains central to our quest to understand the universe and our place within it. Through the atom, we glimpse the infinite possibilities that lie ahead, waiting to be discovered by curious minds. As we delve deeper into the nature of atoms, we confront an even more enigmatic dimension, one that challenges our fundamental understanding of reality, the quantum realm. Atoms, once thought to be the smallest indivisible units of matter, are themselves composed of subatomic particles like protons, neutrons, and electrons. However, beneath even these particles lies a world where the rules of classical physics break down, and strange phenomena emerge, defying our common sense. This quantum world is governed by probabilities, uncertainties, and bizarre interactions, which make it a fascinating yet perplexing frontier in atomic science. At the heart of quantum mechanics is the principle of superposition, which suggests that particles can exist in multiple states simultaneously. This is starkly different from our everyday experience, where objects exist in a single, definite state at any given time. In the quantum world, an electron, for example, can be in multiple positions at once, orbiting around the nucleus of an atom. However, when we attempt to measure its position, the electron chooses a specific location, collapsing the superposition into a single outcome. This phenomenon, known as wave function collapse, suggests that the act of observation plays a fundamental role in determining the state of a quantum system. The implications of superposition are far-reaching. It challenges the very notion of objective reality, implying that the universe operates in a fundamentally probabilistic manner. In other words, until something is observed or measured, its state exists only as a range of possibilities. This raises philosophical questions about the nature of existence itself. Is reality something that exists independently of observation, or is it inherently tied to the act of measurement? Could the universe, at its core, be a collection of probabilities waiting to be realized? One of the most iconic demonstrations of quantum strangeness is the double-slit experiment. In this experiment, particles such as electrons are fired at a screen with two slits. If one slit is open, the particles behave like tiny billiard balls, passing through the slit and forming a pattern on the screen behind it. However, if both slits are open, the particles exhibit wave-like behavior, creating an interference pattern as if they were waves passing through both slits simultaneously. Even more puzzling, when scientists place detectors to observe which slit the particle passes through, the particles revert to behaving like individual particles, and the interference pattern disappears. This suggests that the act of observation itself influences the behavior of particles, leading to profound questions about the relationship between consciousness and the physical world. Quantum entanglement is another mind-bending phenomenon that defies classical logic. When two particles become entangled, their properties become linked in such a way that the state of one particle is dependent on the state of the other, no matter how far apart they are. If we measure one of the particles and determine its state, the other particle instantaneously adopts the corresponding state, even if they are separated by vast distances. This seems to violate the principle of locality, which states that information cannot travel faster than the speed of light. Albert Einstein famously referred to this as spooky action at a distance. And while quantum entanglement has been experimentally confirmed, its underlying mechanisms remain a profound mystery. The study of atoms at the quantum level has led to groundbreaking technological advancements, most notably in the field of quantum computing. While classical computers process information in binary units called bits, which represent either a 0 or a 1, quantum computers use qubits, which can represent both 0 and 1 simultaneously due to superposition. This allows quantum computers to perform complex calculations at an exponentially faster rate than classical computers. Quantum computing holds the potential to revolutionize fields such as cryptography, drug discovery, artificial intelligence, and materials science. For example, quantum computers could simulate molecular interactions with unprecedented accuracy, leading to the discovery of new materials or more effective pharmaceuticals. However, the development of quantum technologies also comes with significant challenges. The quantum states of particles are highly delicate and prone to decoherence, where interactions with the environment cause the quantum system to lose its coherence and revert to classical behavior. This makes building and maintaining quantum computers incredibly difficult. Nevertheless, researchers are making steady progress in overcoming these challenges, and we may soon witness the full realization of quantum computing's transformative potential. In addition to quantum computing, another promising application of atomic science is quantum cryptography. Traditional cryptographic methods rely on the difficulty of solving mathematical problems, but they are potentially vulnerable to the immense computational power of future quantum computers. Quantum cryptography, on the other hand, leverages the principles of quantum mechanics to create unbreakable encryption. One technique, known as quantum key distribution (QKD), uses the properties of entangled particles to transmit encryption keys securely. If an eavesdropper tries to intercept the key, the act of observation will disturb the quantum state, alerting the sender and recipient to the presence of the intruder. In this way, quantum cryptography promises a new era of ultra-secure communication. As we consider the impact of quantum mechanics on technology, we must also confront its philosophical and existential implications. The quantum world seems to challenge our traditional understanding of causality, determinism, and the nature of reality itself. If particles can exist in multiple states at once, what does this say about the concept of free will? Are our choices predetermined by underlying quantum probabilities, or do we have some agency in shaping the course of events? The interplay between quantum mechanics and philosophy is a rich and ongoing field of inquiry, one that forces us to reconsider our most basic assumptions about the universe. At the same time, atomic science connects us to the very origins of the universe itself. According to the Big Bang theory, the universe began as an incredibly hot, dense singularity approximately 13.8 billion years ago. In the moments following the Big Bang, the universe rapidly expanded and cooled, allowing the formation of the first subatomic particles, quarks, electrons, and eventually protons and neutrons. As the universe continued to cool, these particles combined to form the first atoms, primarily hydrogen and helium. Over billions of years, gravitational forces pulled these atoms together to form stars, galaxies, and ultimately the complex structures we observe today. Stars, in particular, play a critical role in the life cycle of atoms. Through the process of nuclear fusion, stars convert lighter elements like hydrogen into heavier elements, such as carbon, oxygen, and iron. These elements are then dispersed into the cosmos when stars explode in supernovae, seeding the universe with the raw materials needed for the formation of planets, moons, and life. In this way, the atoms that make up our bodies were forged in the hearts of ancient stars, connecting us to the cosmos on the most fundamental level. As the physicist Carl Sagan famously said, "We are made of star stuff." The study of atoms also offers insights into the future of the universe. One of the most intriguing questions in cosmology is the ultimate fate of the cosmos. Will the universe continue expanding forever, eventually reaching a state of cold, dark emptiness known as the heat death? Or will it undergo a big crunch, collapsing back into a singularity? The answer to this question depends on the properties of atoms and the fundamental forces that govern their interactions. Dark energy, a mysterious force that appears to be driving the accelerated expansion of the universe, plays a key role in determining its fate. However, our understanding of dark energy and its relationship to atomic structure remains incomplete, leaving the future of the universe an open question. In addition to contemplating the future of the universe, atomic science raises profound ethical and moral considerations. The development of atomic energy, for example, has brought both immense benefits and catastrophic risks. Nuclear power plants generate vast amounts of electricity with minimal carbon emissions, offering a potential solution to the global energy crisis. However, the use of atomic energy in weapons of mass destruction, as demonstrated by the atomic bombings of Hiroshima and Nagasaki, has shown the devastating consequences of harnessing the atom's power for violent purposes. As we continue to develop new technologies based on atomic science, we must carefully weigh the ethical implications and strive to use these advancements for the betterment of humanity. The study of atoms offers a window into the deepest mysteries of the universe, from the behavior of subatomic particles to the origins of life and the fate of the cosmos. Through atomic science, we have gained unprecedented insights into the nature of matter, energy, and the forces that govern the physical world. Yet, despite our progress, the atom continues to hold many secrets, challenging us to push the boundaries of knowledge and understanding. As we stand on the cusp of new discoveries in quantum mechanics, cosmology, and nanotechnology, we are reminded that the smallest things in the universe often have the most profound significance. The atom, once thought to be the indivisible building block of matter, has revealed a universe of complexity, beauty, and mystery, inviting us to explore the infinite possibilities that lie within. The exploration of atoms doesn't stop at our understanding of the quantum world and its implications. As we continue to dive into the intricacies of atomic structure, a key area of focus lies in how atomic interactions form the foundation of chemistry, biology, and even the materials that shape our everyday world. The study of atoms, particularly how they bond and combine, forms the basis of molecular chemistry, giving rise to the substances and compounds that make up the material world. At the most basic level, atoms bond to form molecules through the sharing or exchange of electrons. There are different types of bonds, but the two most significant are covalent and ionic bonds. In a covalent bond, atoms share electrons in a way that allows each atom to achieve a more stable configuration. A familiar example is the formation of a water molecule, where two hydrogen atoms share electrons with an oxygen atom. Ionic bonds, on the other hand, occur when one atom donates electrons to another, resulting in positively and negatively charged ions that are held together by their opposite charges, like sodium and chlorine in table salt. The properties of these bonds, and the structures they form, create the diversity of materials that we interact with daily. When atoms bond together to form molecules, they can create a wide variety of compounds with very different properties depending on how the atoms are arranged and the types of bonds involved. Take, for instance, carbon atoms. Carbon is one of the most versatile elements in the periodic table, and its ability to bond with other atoms in a variety of ways makes it the backbone of organic chemistry, the chemistry of life. Carbon atoms can form chains, rings, and complex structures that give rise to everything from the DNA that carries genetic information to the carbohydrates, proteins, and fats that fuel living organisms. The structure of molecules determines their properties, both at the microscopic level and in the materials we use. For example, the same carbon atoms that form soft graphite and pencils also form the hardest natural substance on Earth, diamond. The difference lies in the arrangement of the carbon atoms. In graphite, the carbon atoms are arranged in layers, allowing them to slide over each other easily, giving graphite its soft, slippery feel. In diamond, each carbon atom is bonded to 4 others in a 3-dimensional lattice, creating an incredibly strong, rigid structure. This illustrates how atomic structure plays a crucial role in determining the physical properties of materials. On a larger scale, the arrangement of atoms and molecules also governs the behavior of metals, ceramics, polymers, and other materials we rely on in modern society. Metals, for example, are characterized by their ability to conduct electricity and heat, thanks to the sea of electrons that flows freely among the metal atoms. This is why metals like copper and aluminum are used in electrical wiring and heat exchangers. Ceramics, on the other hand, are composed of atoms bonded in a crystalline structure, making them hard, brittle, and heat-resistant. Polymers, such as plastics, are made of long chains of repeating molecular units, giving them flexibility and strength. Advances in atomic science have also enabled the development of new materials with unique properties, such as nanomaterials. By manipulating the arrangement of atoms at the nanoscale, just a few billionths of a meter in size, scientists can create materials with remarkable properties that don't exist in nature. Carbon nanotubes, for instance, are made from carbon atoms arranged in a cylindrical structure, and they are incredibly strong yet lightweight. They also have unique electrical and thermal properties, making them a promising material for applications ranging from electronics to space travel. In the realm of energy, atoms are the source of both conventional and cutting-edge power generation. Nuclear power plants, for example, harness the energy released by the splitting, or fission, of heavy atomic nuclei such as uranium. This process releases a tremendous amount of energy, which is used to generate electricity. Although nuclear energy has its challenges, including the disposal of radioactive waste, it remains one of the most efficient and low-carbon sources of energy available today. On the frontier of energy research, scientists are exploring nuclear fusion as a potential source of nearly limitless energy. Fusion is the process that powers the sun, where hydrogen atoms fuse together to form helium, releasing enormous amounts of energy in the process. Unlike fission, fusion produces little radioactive waste and has the potential to provide a clean, sustainable source of energy. However, achieving controlled fusion on Earth has proven to be extremely challenging, and research in this area is ongoing. As we look toward the future, the study of atoms continues to hold the promise of transformative discoveries and technologies. One exciting area of research is the development of quantum materials, which exhibit properties that cannot be explained by classical physics. For example, topological insulators are materials that conduct electricity on their surface but act as insulators in their interior. These materials have potential applications in quantum computing, where their unique properties could help create more stable and efficient qubits. Another fascinating field is the study of antimatter, which consists of particles that are the opposite of normal matter. For example, the antimatter counterpart of an electron is called a positron, which has the same mass as an electron but a positive charge. When matter and antimatter come into contact, they annihilate each other, releasing energy. While antimatter is extremely rare in the universe, understanding its properties could lead to breakthroughs in fields ranging from astrophysics to energy generation. Furthermore, the exploration of atomic science extends to the search for new elements. Scientists continue to push the boundaries of the periodic table, creating super-heavy elements in laboratories. These elements, with atomic numbers greater than 118, are unstable and exist only for fractions of a second before decaying. However, their discovery helps us understand the limits of atomic stability and the forces that hold atomic nuclei together. In conclusion, the study of atoms touches every aspect of the physical world, from the smallest subatomic particles to the largest cosmic structures. It provides the foundation for our understanding of matter, energy, and the forces that govern the universe. Through atomic science, we have unlocked the secrets of chemistry, biology, and materials science, leading to technologies that shape our daily lives. As we continue to explore the mysteries of the quantum realm and the frontiers of atomic research, we are poised to make discoveries that could revolutionize our understanding of reality and our place in the universe. The journey of exploring atoms is not merely about unraveling the building blocks of matter, it is a quest to comprehend the very fabric of existence. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video if you found this video helpful and subscribe to the channel for more such amazing videos.